starting today. And so the homework B1 is titled Lecture B1, which should mean by the end of the day's lecture, you'll have everything that you need in order to complete that homework that is assigned today, but has been available for a little bit now. So with that in mind, there's also an ICA available, ICA B2, that is due this week. So there's a generous drop policy on those, so don't feel like you have to do all of those ICAs. Lab 2 is due this week, already available. Again, no attendance necessary, but this one is going to be much more like, so Lab 1 was much more like the top half of homework B1. Lab 2 is much more like the bottom half of homework B1. So whereas homework B1's hand simulation is going to be asynchronous using an event-triggered scheduling like we're going to start talking about today, the Lab 2 uses a synchronous timing, but otherwise it uses the same logic. It's just what moves you from event to event is a little bit different. So homework B1, like I said, is out, due in approximately a week, upload to Canvas, and so on. So that is the announcements. In other extracurricular news, if you're interested in using the modeling that you learned from this class for something outside of class, then there is this Rockwell competition, this IIC Rockwell Arena competition, up to 4 undergraduate students, plus a faculty advisor who actually could be a TA as well. It's a real world situational case study. The submission can be used for your final project for this class. If you submit it and get selected as one of the first, second, or third prizes, then there's a monetary award, as well as you get flown out to a conference to present your work, and then the selections are made there on who gets the first, second, or third. So if you're interested in that, this is not directly affiliated with this class. It's with IISE and Rockwell, but it is available. Registration is open. I think it was open all of August. It's open through the end of September. So if you have questions about that competition, there's information here. There's also information on Canvas. So you can take a look at that. If Arena, we're not going to actually see in the labs until Lab 5, but you can get access to Arena either downloading onto your own computer if you have either the ability to emulate Windows on your Mac, as I do, or if you've got a Windows machine. Otherwise, you can also use it on the virtual machine. There's a link to Apporto, APPORTO, on the left-hand side of Canvas, and you can go ahead and also access Arena through that interface. And so if you're interested in getting seeing what Arena is like before the labs, you have that option, and then you can think about whether you would like to put a team together for this. So any questions about assignments or anything else? Okay. All right, so recap, we're focusing on discrete event system simulation, otherwise known as process-centric simulation. A key aspect of this is that the system, it's modeling a dynamical system, so a system that changes over time. So we'll talk about how the system having state, and that state changes, at these discrete instants of time. I don't think my pointer is working today, so apologies for that. These instants where the state changes are called events. So that's what we mean by a discrete event system simulation, is that it's a dynamical system whose activity only occurs at these instants that we call events. So time jumps from event to event. We view them as from a process-centric perspective. So that means that the little things that are moving around in the system are not themselves agents. They don't have agency. They're passive elements that are being moved around by the processes around them. So we put all the logic into the processes, not into the agents. The agents are just kind of, if we're little ants, they're the pheromones that we smear on the world. They are kind of keep track of how the system is moving along, but the logic for how the system is moving along is stored in the processes. So if you are building a simulation of this room, you build the logic into the room, not into the students in the room. You then select when students leave the room, when students come into the room, but all of that is being programmed into the room, not into the students themselves. So that's what we mean by it's a process-centric approach to modeling. We have entities. In that last example, they'd be the students. They're the passive things being moved by the processes around. These are sort of the players that move around these kind of board games. So it's almost like the processes are those that read the cards on the board game and move the little meeples around the board game. That's kind of the idea here. So the entities are the things sitting on the board. They can't move unless something moves them. They normally represent real tangible things like students in a classroom, parts in a manufacturing system, but sometimes it's convenient to have fake entities in the case of modeling. A common example is if you're modeling, let's say, a traffic light. So that traffic light needs to shift from red to green and so on. So what you can do is actually build a virtual entity that is like a token that gets passed from the north-south direction to the east-west direction, deciding who is green at any particular moment, and then gets passed back. So inside your model, you have this little entity that is constantly shuffling between these two processes, the north-south green process and the east-west green process. And it just gets bubbled back and forth. Now, this entity doesn't exist in real life, but it's more convenient for us to build a virtual entity in our software model. Most of the entities that we'll talk about in our models will be able to map to things in real life, but occasionally we use them virtual entities just for convenience in the model. So entities are more complex than they originally seem. Attributes are ways to differentiate entities. You can create different types of entities, but sometimes it's more convenient to create one type of entity and then differentiate them by little stamps that you put on them. So you can keep track of, entities arrive at different times. You can stamp them with what time they arrived at your system and then use that later in calculations. So you might have a process that before it chooses what to do with this entity, it picks them up, it reads their arrival time, and it says, based on this arrival time, how long it's been since they've arrived, I'm going to send them through this process. Or based on their arrival time, I'm going to send them through this other process. You can stamp them with history. So, this one has already gone through primary screening. Well, just like in real life, if somebody's gone through primary screening, then the processes around that person at a security line are going to know to maybe prioritize them when they go pushed through secondary screening. So likewise, you can add attributes to entities as they move through the model, and that allows those entities, even though they're all the same type of entity, passenger, it allows them to be handled differently. But sometimes it's more convenient to split them up into different types of entities. So rather than saying we have one order type, and that order has attributes, whether it's a mobile order or not, we could say we have a process that generates mobile orders, and we have a process that generates in-person orders, and there's separate processes. And which one's better might depend on the rest of the model. So you have a lot of flexibility here. But this is one of those tools you have, the attributes. So these are common attributes that every entity is going to have in Arena. An arrival time, Arena already records the arrival time for you. A priority, you might add a priority to it, and actually think Arena's got a place order for that. Arena's got a color that automatically comes with these, and then it actually visualizes that color for you. So when you change the color attribute, then suddenly the thing that is representing that entity in the sim changes color. And then you can add your own, like due date. So you can say when this entity comes in, this order, an order was generated at this time, but this order is a special order that has a due date, which is next day. And so that might change how it's prioritized downstream. So these are examples of some attributes that you might stamp onto entities. They ride along with the entities. So they're little variables, they can be changed. They ride along with every single entity. So if you're familiar with object-oriented programming, you can think of these attributes as attributes or members of the instantiations of the class that is the entity. And so if you have a person entity, you might have a person A is an instantiation of that. Person A has their own set of members or attributes, and person B has their own set, and person C has their own set, and they're independent, so they're not tied to the global world. There are global variables of the simulation that you also have access to, and you can set, create, and so on. But these ride along with every entity. That's what an attribute is. We have resources. These are the most important thing in a discrete event system simulation. These are things that as you move from Arena to other simulation platforms like FlexSim and Simio, these are things that the other things might change what they're called, but resource, this is a term that you'll see usually across all simulation platforms, because that's really what drives discrete event system simulation. These are the things that entities compete for access to, and because there's a finite number of them, they create delay. They create waiting time. So there was a great question at the end of last class. They said, if I was modeling a restaurant, I might have, let's say, chefs and waiters, and then I've got the customers. And so are waiters better modeled as resources or as entities? And my answer was that unless you're modeling something that affects the experience of a waiter, for example, a waiter might come in and they might have to clock in. They might have to get access to a particular aspect of their uniform. They might need to get these other things. If you're trying to reduce the delay that a waiter feels when they come to work, then the waiter is an entity. But if you're viewing the waiter as something that the customer needs to get access to in order for the customer to get their job done, then the customer is the entity and the waiter is just another resource. So the customer, before they can put their order in, needs to get access to a certain set of waiters. There's a finite number of them, so that makes them resources. The waiter puts the order in. That order then sits and gets delayed because it needs to wait for a chef or other kitchen resources to become available. Those are all resources. Once the food is prepared, then it gets to sit there because what does it have to wait on? A waiter to bring it to the customer. So at different times, the waiter is generating delay. And that's why we view the waiter as a resource, because they're generating a different experience for the customer. And we're focused on the customer's experience. So the customer is the entity, the waiter is the resource. So people, equipment, space, those can all be resources. We view when a entity enters a process, in order to do work in that process, generally speaking, it has to have a resource temporarily assigned to it. But once the work is done, we usually think that that resource is then removed from the entity and put back into the process so the entity can leave and a new entity can enter and then get temporary assigned that resource and so on. So this resource kind of stays while the entities just keep going through. And you can have resources in several units of capacity. So when I talk about waiters and chefs, I could say there are 8 waiters and 3 chefs in this restaurant. In my model, I could actually model 8 separate resources for so 1 per waiter. Or most discrete event system simulation tools will say, what's the type of resource? And you say, well, it's a waiter type. And then it'll say, what's the capacity? It has a capacity of 8. So at that point, anytime you go into a resource where you need a waiter, you ask the sim system, can you give me a waiter? I need 2 for this customer, or I need 1 for this customer. And then it will come back and it'll say, let me see if there's any waiters available. And then it'll look into that pool. It'll say, I'm sorry, right now we're using the full capacity of our group of waiters. You're going to have to wait. And then it waits, and it's the first one in the queue to get that next waiter or waiters when they're available. So we don't always have to model every resource as a separate thing. We can model them as a group that has a size, and that size we refer to as capacity, several units of capacity. So, and that's what's nice about that is it makes it very easy to change how many resources are available during the sim. So in a later lab, you're going to work with scheduling capacities. So you can say that at certain times of the day, this factory or this restaurant, we'll stick with a restaurant example, at this time of the day, we've staffed 10 waiters. At another time of the day, we've staffed 1 waiter. So now the interesting design parameter is staffing. How often do you schedule how many of that resource? So that becomes something that you can very easily change when you model it as capacity. If you had to keep a little waiter node for every single waiter, it becomes much more difficult to programmatically change how many waiters are available. But if you just have a general waiter resource type, and if this capacity, then it's easy in the arena to say, well, right now the capacity is this, right now the capacity is this, and so on. And that's also nice because then, as we'll see here later in this presentation, then you can start asking questions about utilization. So right now, how many of my waiter resource am I using? And so if I have 8 waiters and I'm using 7 of them, then I am at very high capacity. But if I have 80 waiters and I'm using 7 of them, then I'm at, very low utilization. So, and if I had 7 waiters with 8 capacity, that is high utilization. If I have 7 waiters with 80 capacity, that is low utilization. And so by looking at these utilization stats, then it tells me, have I overstaffed? Do I have too many resources? Am I paying too much for this resource because there's just too many sitting idle? So those are sorts of things that once we have the notion of capacity, we can do these better stats. Any questions so far about this overview of these terms? Entities, resources, states, events, and so on. Okay. So to twist things a little bit, when we're thinking about models, sometimes we want to think about our reference frame. Entities traditionally, in the examples that I've given, are the things that move in the real system. So a customer moved into a restaurant. As the restaurant stays in place, the customer leaves the restaurant stays there and becomes available for more entities to come into the restaurant. That is traditionally the way we think about entities and resources. But that isn't the only way we can think about them. Sometimes our limited resource in the physical system actually is the thing moving, and it is encountering stationary entities. And the simplest case of this is modeling like a robot vacuum cleaner, like the one you see up here on the screen. So if you think about this vacuum cleaner is a finite resource. We would like this vacuum cleaner to be everywhere in the house, but it can't be everywhere in the house at once. So certain parts of the house have to wait for it to come and arrive. Now, you might be trying to think of a way to model this as an entity because it's moving, but instead we can think about, well, as it's moving around, what if we sat on top of the robot vacuum cleaner and experienced the world from that reference frame? As far as the robot's concerned, if it didn't know about its motors, the robot would think that the world is moving to it, that the dirt is moving to it. And at that point, the dirt becomes the entity and the robot becomes the resource. And that is a much easier way for us to model these types of systems where the resource gets to move around, but it's the finite resource. We can say, based on whatever movement plan has been implemented on the robot, then what on average is the encounter rate with dirt in the house? And based on that encounter rate with dirt, we can start, modeling, how quickly does the robot's internal container fill up, and it has to go back to its station and empty, for example. We can start modeling those sorts of things, but we don't have to model the robot moving around. We can model it as if it is a factory where dirt is arriving and getting transformed by the factory into clean. And periodically, the whole factory has to shut down while the factory cleans itself. That's basically what's going on with the robot. So in that particular case, it actually is simpler to model in Arena the resource as being the thing that is stationary, even though in the real world it is moving around. And I've done this in a bunch of different models that I've used in research and applications. So from things like modeling. So I used to, when I was in grad school, I would study how animals move through forests and make decisions, and then I would use that that logic, and then I would put it on robots that would travel undersea for exploration. I would put it on military vehicles that would achieve military objectives, or humanitarian vehicles that would achieve, dropping food, for example, things like that. And they would have to make similar decisions as these animals. And in all of these cases, and also flexible manufacturing systems where you have different elements of the factory can make decisions about whether they let a part pass or whether they decide to take on and work with the part right now. And in all of these cases, in the real world, maybe except for the flexible manufacturing system, in the real world, we're thinking about the finite resource as, and in the animal case, we're thinking about the wolf as the finite resource, or the quail as the finite resource. And in those cases, in the real world, it's moving around and it's encountering objects at a particular rate due to its own movement. But when I would model them, it was much more convenient for me to model them as stationary, experiencing a world that arrives at them, and they have to make decisions as these opportunities arrive. So that's an example of using this in the real world on real applications. And that I didn't use ARENA for that, but I did use effectively a discrete event system simulation, or mathematics of discrete event system simulation, to understand these systems. But I modeled the resource as being stationary, even though in the real world it was moving. So that is something you can do. Switch, your reference frames when you're doing these models. Okay. Questions about that? About the different flexibilities you have when choosing entities and resources. Key point is resources are finite, entities are theoretically infinite. There's just a stream of them coming, and we're slowing them down because they need access to resources, and those resources are finite. Okay, great. All right, so then state variables, this is how we do our bookkeeping. So we have to keep track of how many resources are currently being used. We have to keep track of where entities are. Are they in this queue or are they in this queue, and so on. All of this bookkeeping to keep track of the state of the world we put into a so-called state variable. So, the clock is actually the current time. You can actually view as a state variable as well. What is the current time in the world? Usually our models don't care about the absolute time. They care about the relative, how much time has passed. But we care about the absolute time, how much time since the beginning of the simulation. And so clock is a state variable. There are lists that are state variables. So what is the current list of entities that are standing in line right now? That's an important state variable. There are a number of entities waiting in the queue. Instead of keeping track of the whole list, we might just keep track of how many entities are currently in the queue. We might need both, and so on and so forth. And so these state variables are often going to change during those events. So an event is an opportunity for one of these state variables to change its value. Their values are the states, but their names, which you can use in logic, for example. So you can actually make a system dependent upon its state variables. So you could say, well, when the Q is less than 8, then we get a certain arrival rate. But when the Q is greater than 8, we get bulking, BALK, bulking, like people see that the long line and they go elsewhere. So we see that we might have an arrival rate of 1 customer per hour, or 1 customer per 10 minutes if the line is less than 8. But once the line is over 8, then we only see 1 new customer every hour because people see the long line and they go elsewhere. So we can add that logic, we can make that logic conditional on the state of the world. And so these are the things that go into those formulas when we're coming up with those arrival rates. We can make them conditional on state variables. Activities versus delays. I've already kind of beaten you over the head with this, but this will be something that it is difficult to see the distinction at first. So I'm going to keep belaboring this. An activity is a duration that we know ahead of time without running a simulation. I don't mean we know it in a deterministic way, but we know its statistical distribution without running the sim. So we know that there is a distribution of times that it takes for buses to arrive at a bus stop. And so, there might be a bus might take anywhere from 9 minutes to 11 minutes to arrive at a bus stop. It could be anywhere in that range. but the time it takes to arrive at a bus stop, where we might assume has nothing to do with how many people are waiting for that bus. If that's the case, then it's probably best to model the waiting time for the next bus as an activity, because it doesn't depend on the state of the simulation. So anything that you can look up in a table before you run the simulation, that's an input to the simulation, and that's an activity. The flip side of that is the delay. How long did you wait for that bus? And it might be that the bus only had 10 seats left on it, and there were 15 people waiting at the bus stop. So now 5 of those people couldn't get on the bus, and they have to wait for the next bus. And so they've now experienced a delay, which depended upon the state of the system. If there were just fewer people ahead of them, they could have gotten on that bus and they would have experienced less delay. So delay is something that, if there's no way you can predict the delay by ahead of time, where you have to run the simulation in order to figure out what the delay was. You have to play the game out and see what the scores are at the end of the game. That's an output, and outputs are delays. So activities are inputs, outputs are delays. Any questions about that distinction? It's really important. You're going to see it over and over and over again. Yeah. Yeah, that's right. A way to say that is a delay is a wait time that is unpredictable, that requires you to run the sim to get any idea of how long that delay is going to be. Whereas an activity is something that ahead of time, if somebody asks you, when you get up to a clerk at a bank, about how long is it going to take you to cash a check? Well, they can say, well, I can look that up. But like, it's going to take me anywhere from 30 seconds to 5 minutes to cash a check. And I have a distribution that's going to shaped like this. It has this mean, it has this variance. It has nothing to do with how many other people are at the bank. Once you get up to that clerk, then it has nothing to do with the rest of the bank. The clerk is there, you're there. And at that point, there's a certain amount of variation that's just in the system that has nothing to do with the state of the system. Now, if somebody asked, how long is it going to take you to get up to the clerk? Then you have to say, well, how many other people are in the bank? How many people are ahead of you? Did you arrive first? Did you arrive last? Was it at lunch? There's all these other questions that you have to ask. And these questions often will have to do with other customers at the bank. And if it has to do with other entities, if one entity's experience is affected by the experience of another entity, then we're probably talking about a delay. All right, any other questions about that? Activities versus delays. Inputs versus outputs. Okay, so activities can be variable, but we've got stats. A delay for one entity is often an accumulation of activities experienced by others. That's what I was just said. Okay, questions about that review? All right. So the other thing that I wanted to get to last time, we didn't quite get there, was this notion of stochasticity. And I've talked about randomness a bunch so far. And this is a perspective for modeling variation in the world. So we have people arriving to an airport, different groups of people have different numbers of people in their party. And those parties are separated by different amounts of time. And there's variation in the time between those. We can claim that there's roughly 5 passengers arrive per hour. So there's roughly 20 minutes between every group of passengers. But that's not, they don't arrive on a conveyor belt with that regular spacing. They have irregular spacing, and so they have real variation. So we want to capture that realistic variation in our models. And we're going to do that through so-called stochastic modeling. Stochastic is not a synonym for random. A lot of people think it is. Stochasticity or stochastic is an approach to using randomness in order to make it simpler to model variation. Stochastic comes from the Greek word for guess or conjecture. So when you look at data from an airport and you see how apparently random individuals arrive at the airport, you just say, it's going to be much easier for me to model arrivals of individuals to the airport as if they're random, as if some quantum mechanical dice were thrown in the universe that caused these people to pop into existence at random times. That is not the real process that's going on. We know that there are deterministic reasons why one person arrives 5 minutes after another person, and the next person arrives 7.5 minutes after that, and so on and so forth. We can trace that back. There's no randomness in the real trace of that. There are real reasons, and that every single aspect of it is predictable if you have enough information. The problem is we don't have enough information. So we factor out all of the information we don't have, and we view it as noise. That unknown information is noise that's been added to our system. And we then say, well, what can we do with that noise? Well, let's just assume that that noise is just part of the universe. Like I said, it's just like quantum mechanics or something like that. We're going to just make the guess or the conjecture that the process is random. We don't care that the process is actually not random, but it is a good modeling tool, because now, instead of having to deal with all of that information that we might need to know, why did the Jones family arrive at a particular time and the Wilson family arrive at another time? Rather than having to go through all of that detail, we can just say, you know what? All groups that come to the airport, they just arrive according to looking at our data. There's a distribution, a probabilistic distribution that seems to match how they arrive at the airport. And that distribution has 1, 2, 3, 4 parameters, but that's all I have to worry about. Normally only 2 parameters. I might need just a mean and a standard deviation. Or maybe I need a skewness or something like that. Maybe I need 1 or 2 more parameters, but usually I only need probably 2, sometimes as little as 1 parameter. And I now get all the variation for free. And so that's what stochastic modeling is using randomness to reduce the burden on what information you need, because you replace it with a probability distribution that has 1 or 2 parameters instead of thousands of parameters that you need to actually come up with the story of the Jones life or the story of the Wilson's life and so on. That's what we mean by stochastic modeling. And that's the modeling that we use in discrete event system simulations. And so we're going to gradually learn how to trickle in that randomness. In the first homework that you get, I'm going to give you a list of numbers that have to do with how long in between customers that arrive at this system that you're modeling. That list of numbers is just provided to you, but you can think of that as being generated by a random number generator. And that's what we're going to gradually move into, the point where you're not going to worry about getting lists from me. You're going to get parameters from me. And then from there, you can just draw random numbers according to those parameters. Just like whenever a board game tells you to roll the dice, they say, roll the dice and then look at a card and say, based on the number that you see, there's certain outcomes. That card is going to be the logic that you program into the computer. And the rolling of the dice will be the random number generator that the computer gives you. And so, we can, that card makes the board game have outcomes that feel realistic, even though they're determined by a roll of a dice. The random number generator in the computer, plus the logic that you craft based on the outcomes of that random number generator, will make the simulation look real, even though fundamentally it's random. That's what we mean by stochastic modeling. And that's what we do in here. Now, I've mentioned that activities are the inputs. The term we use in these systems, and this is not a term that I came up with, this is a term that is used across discrete event system simulation, is input modeling. That is the choice of these probabilistic models for these activities. So the choice of that card in the board game that says what to do with the random dice throw, the choice of the logic of what to do when you randomly generate a number between 0 and 1 in order to generate a time in between one group and another. That is what we refer to as input modeling, coming up with those parameters, with those distributions. Okay, questions about that? Now, of course, I said stochasticity is not a synonym for randomness, but people are going to use it that way, and it's a convenient shorthand. But once upon a time, randomness has existed for hundreds of years. People have been talking about randomness. It wasn't until like the early 1900s until this term stochasticity came into play. And it was because people were writing a paper where they said, hey, we notice we get a lot more traction if we assume this system is random, even though it's not. And we're just going to make a guess that it's random. And that's why they appealed to the Greeks and they said, all right, the Greeks have a word for this, so we're going to call it stochasticity. That's why if you look up the etymology of stochastic, it comes up to guess or conjecture. It has nothing to do with randomness, even though people often view it as a synonym for randomness. Clear? All right, great. All right, so I already sort of said all this. The advantage, it simplifies the implementations. The challenge is now you guys got to know a lot more about probability than your average modeler that's out there. So you got to know about probability, you got to know about parameterizing probabilistic distributions. You have to also, this is the crazy thing, is that we're going to build sims that are just as unpredictable as the real world. So just like in the real world, you can have good luck and bad luck. You can say, wow, we had a really good day at the Chipotle or something like that. We all of our customers had like 0 wait time and it was a really good customer experience day. And then you could say, well, what did we do today that made it better? And somebody might just say, well, you know what? It was just good luck. We just happened to have a decent amount of spacing between customers that we didn't get a lot of queues forming, and it was just a good luck day. Tomorrow will be a different day. And so to test that hypothesis, you have to see, will tomorrow be a different day? And tomorrow, maybe you don't get as good stats. So that's good luck versus bad luck. That's why you have to run multiple replications to test your intervention. Did I make a difference at the Starbucks of the Memorial Union? You aren't going to know over 1 day's time. You're going to have to run that for 5 days, maybe 5 weeks in order, and then look at the stats over that and compare that to the stats from the previous 5 weeks, and then control for seasonality and all that sort of stuff. We have to do that same level of replication with our computer models because we've introduced randomness. Because every time you run your model, you get a different result. And that has the benefit of looking realistic, but has the cost of meaning that we can't run the models just once. We have to run them multiple times and then do stats. So we have to do a lot more work after the sim in order to make the sim simpler and also more realistic looking. Okay, so that's that. I've mentioned this before. The activities are inputs, delays are outputs. That's the reason why we call it input modeling. So choosing of your input models, like, is the spacing between passengers at an airport, is it an exponential distribution? Is it a normal distribution? Is it a beta distribution? If all of these things you can put in to Arena and run your airport sim, you will get different outputs for each distribution choice. One of those outputs might make your airport look really good. The others might make them look really bad. So even though your airport model looks, looks defensible, like it looks like an airport, the X factor, the thing that differs, are the probability distributions you put into the inputs, into the spacing of passengers that arrive at the airport. So if you get those wrong, you'll get bad outputs out. And so this is why, I put this up here about fashion models. And actually now with the Sydney Sweeney commercial, this feels very salient, right? Jeans versus jeans, G versus, G jeans versus J jeans, here you're saying if you're only looking at the model, so if you're only looking at the G jeans, then it doesn't matter what the clothes look like because they're going to look good regardless. And so that's a bad choice of input model because your customer is going to say, hey, I had a good reaction to that output. So that must mean that the intervention you defined, the clothing that you provided for me, is good clothing or good intervention. But if the only reason it looks good is not because of the system changes you made, but because of the person or the data that you wrapped it around, then in that case, you can't trust the outputs. So if you're advertising that your product only looks good because of the person who's wearing it, then that probably means it's not a product that other people should buy. But if you have good input models, so if you can say, look, the types of passengers, the delays that we see coming into our model look just like the delays or sorry, not the delays, the activities we see coming into the model, the durations between passengers, the numbers of passengers, all of these distributions that could vary that are coming into our model, all of those look like data from history, from current trends, or whatever. They all match. And given that those all match, they're representative samples, we take all those and we pipe them through the airport model, and then suddenly the output variation we now might be able to trust. We could say, given that you gave us good inputs, given that your flow chart looks like a real airport, like it looks passable, it passes face validity, I get the two of those things together, and the outputs I now can trust. So if you show me outputs that show an improvement in performance, then I can trust them because I trust your inputs. Whereas if you just show me inputs that are like good luck inputs, like, yeah, if anyone had those inputs, any airport would perform well, then it doesn't really tell me anything about the outputs. So input modeling, or the so-called garbage in, garbage out that we talk about in simulation modeling or modeling in general. So you want to make sure you don't have garbage in, so you don't have garbage out. So we are going to try to capture accurate models, but then we're also going to have replications of our outputs in order to make sense of our models, because we have randomness on the input, which means we're going to have random variation on the output, which means we have to run the output multiple times in order to see if the result we got was not just a good luck result, it was a generalizable result. So that's what we do. Questions? Okay. So that brings up, I would normally, I'll just keep going, and then I'll do the next clicker. So let's do time. So now getting to, I want to make sure that you've got the tools that you have to start working on homework B1. And the key part of the hand simulation in homework B1 is how to move time from one point to another in a simulation model. So you're going to be doing this by hand. So we have to understand, how does time move in these simulations? So what do I mean by that? Well, and a lot of times when you think about simulations, if I simulate a system, a lot of times the easiest thing to think of is I'm just going to simulate what happens at time 0, time 1, time 2, and I separate everything by exactly 1 second. That is one way that you can set up a simulation. That's not how we set it up, because that would be inefficient, because it may be that like if I were to wait for the next arrival at this door, that may take a huge amount of those steps. If all I care about, if I'm modeling the how much this room is being used, all I care about are when the arrivals happen. I don't care about what happens between the arrivals. So I can be much, much faster if I can manage to jump from arrival to arrival to arrival. And so I can jump over all these steps. And so that's the worldview that we're going to have. It's the so-called event scheduling worldview, where our sims only jump to points of time that potentially could change the state of the world. We don't care about any increments of time where the world is constant. And so we skip over them, and it makes our sims faster. So how does that work? So events, we know, are points in time where the state changes. Time is going to move in irregular jumps. It's not going to move in steady jumps. And simulation is going to iterate through what's going to call the event calendar. So in order for us to know, and this is what you're going to hand simulate on your homework, in order for me to know that, like, if I'm really only care about the time where the next arrival comes through that door, then when the previous arrival came through that door, I need to schedule the next arrival on my calendar so I know where to jump to next. That's where I consult my activities, and I say, okay, so I know that there's a distribution of time in between arrivals. Now that I've gotten one arrival, I'm going to draw the duration between that arrival and the next arrival. And I'll say, okay, in 7.5 minutes, I will get another arrival. So I'll put that on the calendar. And it may be that I have other things on the calendar before that 7.5 minutes. I don't know. All I know is I'm going to schedule it on the calendar, and then my next thing will be I'm going to jump to whatever's next on the calendar. It might be that next arrival, or it might be other things that I've scheduled. That's what we mean by the event calendar. We're going to step through an example of that. So at each event, we go from simulation clock, we go from one point to the next point to the next point, jumping through irregular steps. We execute event logic. So what just happened at that step? Somebody came in. We're going to increment the number of people in the room. That's our event logic. Now, in order to keep the sim going, we need to schedule that. Oh, an arrival just happened. Well, I need to schedule the next arrival. So those are the three steps. We do at every time step. And that's how we build the event calendar as we simultaneously move through it. So this event calendar is something that the computer scientists would call a priority queue. It is sometimes also called an event list or a future event list or just a schedule. So if you go to in your textbook, it's called a future event list. In Arena, it's called an event calendar. In other simulation programs, it's just called a schedule. So there are different names for this, but all discrete event system simulation tools have some notion of this, and it's all a so-called priority queue. So the two fundamental operations, you can always get the next time out, and you can always insert an event at the right position. But otherwise, the simulation doesn't have access to the event calendar. I think I might say this here. You, the programmer, while you're debugging, you can see what's in the calendar, but you can't depend on it like a state variable. It is not a state variable that you can use. You cannot look ahead and say, hey, before I execute some logic right now, what are all the things that I know are going to happen? And based on those, let me change the way I'm executing the logic right now. You can't do that. All you know is what is currently now as the program. As a programmer, you can look at the event calendar and see if something's going wrong and how things are being scheduled. But the program only knows what's currently happening right now. So it doesn't have access to the event calendar. Okay, this will make more sense, I think, as we go through an example. So here's an example of simulating a car wash. We've got an entity arrives at the beginning of the car wash. It needs access to the actual car wash, and it might need access to vacuums. These are finite things that always exist at the car wash, so they're resources. Whereas that is our entity that you enter and eventually you leave. So the cars are the entities, and these are the resources. So we would like to figure out how long, for example, the average car has to wait. So we're going to simulate a bunch of cars going through this process. So this will be the eventual event calendar after we're done. So as you can see, we've got arrivals, we've got events where they enter the wash, we've got events where other cars arrive, events where cars have left. This car is going to be ready to go to the wash, but it can't go into the wash because the wash is busy. We've got, the wash is now free because the car's exited, and so on and so forth. So these are all things that change the state of the world. So how do we generate this? Well, at first, all we know is that we get an arrival at time 0. So we jump to the first arrival. And now we have to think about, well, what happens? What's the event logic that happens at arrival? Well, assuming that everything's empty, then this car can enter the wash immediately. So when they enter the wash, we're going to schedule that they're going to enter the wash. Now they have to drive to get to the wash. So there's a little bit of a delay as they go from the car wash entrance down. That's a transport delay as they move to the beginning of the car wash. So we scheduled that event. We scheduled, what's going to happen. We know in the future that it's going to eventually hit the car wash. We're going to deal with what happens when it hits the car wash when we get there. But right now, we're just scheduling that we know it's going to happen. Now, we just processed that arrival. So the last thing we need to do is schedule the next arrival. We have a distribution of this duration, of this inter-arrival time. So we're going to consult our probabilistic distribution. We're going to draw from it. We're going to add that amount of time, schedule when car B arrives, and now we're done. So now we can step through to the next thing in the calendar, which just in this case happens to be car A entering the wash. So now we have to do the event logic. For this particular event, when you enter the wash is free. So the next thing that we know is going to happen in the future eventually is you're going to exit the wash. Assuming the wash doesn't fail. If it does fail, we can schedule that, but we're not no failure model. So all of this car wash doesn't fail. So if you enter the wash, you will exit the wash. And there's a duration of time that we know of that will be how long it takes on, for this car to get out of the wash. Some cars will be slower, some cars will be faster. We can draw that from a distribution. So we'll schedule when it exits the wash. So that's the time we scheduled here. Going to exit the wash there. So at that time, so we can, keep track that now during this period of time, the wash is busy. So if we have a state variable that keeps track of how busy the wash is, we might change that state variable too. Keeping it simple here, I'm not going to show that stuff, but we're probably doing that as well. Now we're done. There's no other events we have to schedule. So then we jump to the next thing in the calendar, the car B arrival. Now remember, I just said the car wash is busy. So when we jump to the car B arrival, we can't, we have to schedule. I was jumping ahead. I was looking ahead in the event calendar, and I shouldn't do that because I forgot that I have one other thing that I have to do. So when the car B arrives, I have that transport delay. So when a car B arrives, the first thing that I do is I schedule how long it takes for it to actually get to the car wash inside the complex. So I schedule that transport delay, and then I potentially schedule when car C arrives. I'm not doing it here just for simplicity, but in order to keep the system going, whenever you get an arrival, you always have to remember to schedule the next arrival, or else it will never happen. This is your one opportunity to make sure that you get another arrival. If you forget to do it here, you just run out of arrivals. So somewhere down here, we're assuming I scheduled car C arriving. So then I jump to my car B being ready. Now here, I know the car wash is busy. I kept track of that in a state variable that I haven't updated here, but we know just by looking at this that the car wash is busy. So at this particular point, car B can't schedule its exit. Now you can say, Ted, I know car B is eventually going to start its wash here. So can't I just shortcut and then schedule car B's exit at this point? And no, you can't take those shortcuts because the computer, which will be the thing actually doing this, it's not as clever as you. It doesn't look ahead and try to do those shortcuts. And you're going to have such a complex system. There'll be multiple arrivals happening in parallel. You actually don't know that nothing is going to get inserted here. So there could be maybe a car Omega that we didn't see. It was before this that it now, something happened and it now didn't get prioritized and it gets pushed in front of car B. And, and that just happens randomly. It happens spontaneously. That could happen. So we always can only do the next thing on the calendar. So at this point, we just have to say, car B, you get to wait in line. So we're going to probably have a state variable keeping track of how many cars are in line. We're going to add B to that line. And then we're just, so we add them to the queue. We say Q, B is in line. And then that's all we can do. So we've added them to the line. So finally, then we can jump to when car A exits the wash. Car A exits the wash, freeing up the wash. So now at this point, we can move, as we'll see, car B out of the line into the wash. And then now we'll schedule car B exiting the wash. This amount of time here that car B had to wait, that is an output of our simulation. We have now discovered that cars wait. We have now discovered that cars arrive fast enough that sometimes cars wait. And this example waited this much. We did not know that ahead of time. That is a delay. Delays are outputs. So we move ahead. We schedule that when car A exits the wash, there's a transport delay when it enters the vacuum. We now know that car B was in the queue, so let's move car B out of the queue. And now let's schedule when car B exits the wash. And now car B is exiting the wash. Our next thing will be to deal with car A at the vacuum and so on and so forth. So I could keep going through this and so on. And then eventually I get to that event calendar that I said we would build. Questions about that process? Yep. So I'm saying like we are the global timekeeper. We are some omnipotent Marvel entity that gets to schedule when things happen in the universe. And so to us, it's just putting it on a calendar. We're just scheduling. We're saying in the future, this is going to happen. So this is happening inside the simulation, is that whenever a certain event happens, we tell the simulation what distribution to draw from and what to add to its event calendar. So you're going to do this by hand on your homework assignment. And so what I'm just saying is like this timeline, this is where all the states change in the simulation. So the simulation iterates through these 1, 2, 3, 4, 5, 6, 7, maybe more steps. This is the only time that interesting things happen in the simulated world. But we don't know where these 7 points are ahead of time. We only know at the start of the sim where the first point is. But we use the things that happen at the first point in order to place points further down on the line. And then that moves the sim to them. So when I say schedule, all I'm saying is we're placing these points on the line. We don't know this ahead of time. So we have to go through a process like this where we currently are, we can now schedule ahead new things that we know are going to happen. At the start of the sim, we have no idea what's going to happen except that an entity is going to arrive. Well, it's not arbitrary. It's based on our input models. So we know that there is a distribution of time in between cars that arrive. So when we have an arrival, before we can leave the arrival, we have to then draw from that distribution to say, if there's an exponential distribution of inter-arrival times between cars, I'm going to draw from that exponential and I will get 3.1 minutes. And then I place a point 3.1 minutes out here. When I process this arrival, I'll draw from that random distribution. It'll come back 2 minutes. And then I'll put a point 2 minutes out here, and so on and so forth. So it's not arbitrary. We're saying ahead of time, somebody has stood at the car wash entrance and with a stopwatch, and they've come up with this distribution. And so we are saying, based on the data we have up at the car wash, we're going to generate inter-arrival times that are consistent with that data. But we only generate them one at a time. And so we generate this one, and when then we process this one, we generate a new one. We process that, we generate a new one, and so on. Same thing with the car wash. Somebody sits at the car wash with a stopwatch, and I used to make students do this in some of the other courses that I taught. And then as a car would go into the car wash, they would keep track of the start time. When it came out of the car wash, track the end time. And then you looked at that distribution, and that distribution would be the time that we're going to space whenever car A enters the wash. We then schedule from that distribution when it's going to exit the wash. Other questions? Step through that all again. Okay. So these inter-arrival times and service times, for now, on your homework, I provide you to them in a list format. Further on in the class, we're going to draw them from random distributions with parameters that, as we'll talk about later on in the class, will be grounded in data. So someone goes out and they actually gather data on these real durations or real numbers of like how many people are in a party, for example. They'll gather those real data. That will we then fit a probabilistic distribution to the data, and then we draw random numbers from that fit distribution. And that's how we actually do it. But to start on your first homework, I'm just going to give you that list as if I did that process for you and I drew 8 numbers from those distributions already. And you just have them in a list. Okay. All right, so questions about any of that? Good, all right. So just to generalize that, your homework is going to deal with a very similar system where we've got an arrival. So if in 470, you'll learn about Kendall's notation, like MM1s and things like that. And you might see queuing network nodes like these. You're not going to need to know these very much for this class, but occasionally I'll put up diagrams like these just because they're very common. So this diagram means that I've got a certain process that is generating arrivals to a system. Those arrivals have access to a single, so they arrive at a rate lambda. So that rate could be arrivals per second, so 5 per minute or something like that. There's a service parameter. So this might be the average time it takes while you're in a server. So this server on average takes 3 minutes to complete its service. And in between them, you have a queue. That's what's here. And that queue, if the server is busy, then you get added to that queue. That's what that symbol means. So it's a generic way of talking about a node in a queuing network. And so when we simulate a queuing node like this, which is effectively what you're doing for your homework, that this is the logic you go through as you do the hand simulation. And so initially, you schedule the first arrival like we did in the car wash example. So you're going to schedule it to occur at a time instant. The simulation starts. We usually just call that time 0 arbitrarily. And then you oftentimes will also schedule arbitrarily an end event. Now, this end event usually is just how long you want the sim to run because you don't want it to run forever. So you're going to say, I know the sim might actually, like the real system might keep going on, but I am only going to simulate an hour of simulated time. And that's what the end event is. So initially, you have 2 events on your event calendar. The first arrival and the time that you're going to say, I'm done simulating. But that is just an arbitrary end point so that you can get your computer back, so they can actually finish the sim. So you do that, and then you continuously process scheduled events. And every time you schedule events, you process events, sorry, every time you process an event, you are almost always going to schedule more events and so that the simulation keeps going. And those events come from distributions, which have been parameterized from real data. Okay, so we're going to talk about there being only a couple events that we have to deal with, and we deal with them in different ways, as we saw with the car wash example. One of the events you might see that you're like, you jump to the next event, and you have to ask, what type of event is this that I jumped to? If it's an arrival event, then the first thing we do, as we do with any event, is we move the clock to that time. It is now the time of the event. At that time, then if it's an arrival event for a queuing node, then the key question is, can we give this entity directly to the server? Can we just skip the queue and bring it into the server? And so the question we ask, is the server available? Are there other entities ahead of this entity? And if it is available, we move the entity directly into the server. And when that mu comes into play, that mean server time, that is what parameterizes the distribution that we're going to use to schedule how long our entity is going to be in the server. In other words, how long the server is going to be busy. And we will schedule that event to happen. And at that point in the future, it will become free and another entity can move in. So that's what I'm saying here. We're creating a departure event that we schedule in the future. Now, it may be that the server was already busy. In that case, we can't schedule anything because we have no idea when things are going to end because we're not allowed to look ahead in the event calendar. So at that point, all we do is we add the entity to the wait queue. And so you add the entity to the wait queue, and then and that's all you do in terms of logic. So now we go back into the generic things we do for any arrival event. Because we got an arrival event, if we want to get arrivals in the future, now is the time to schedule them. There's no other time that arrivals can get scheduled. So we have to draw the inter-arrival distribution. We have to draw from the inter-arrival distribution that we've been provided from data, and we're going to schedule the next arrival. And at that point, so we schedule that, and then there might be some stats we might want to keep track of. So there might be some marginal stats that, for this particular event, how much of this happened or how much of that happened, things that help us do bookkeeping later. But then we're done with that arrival event. So then we move on to the next event. The next event could be an arrival event, in which case we went through the same steps. Or the next event could be a departure event. So for a single queuing node like this, then departures are going to happen. On a departure event, just like in the arrival, we move the clock to that time. And then at that time, we ask, is the wait queue empty or not? If there's entities in the waiting queue behind this entity, we can immediately move them into the server. What does it mean to move them into the server? It means we can schedule their departures. So from this departure event, entity one has departed. We can now schedule entity two's future departure because entity two is immediately ready to move into that server. So we schedule that, we create a departure event in the future, and then we update statistics, and that's all we do. So if nobody is around on a departure event, so if the queue is empty, we don't do anything. We just let it sit. There's nothing we can schedule. If service is ended and there's no entities waiting in the queue, we have no idea what's happening in the future. We have no ability to schedule anything into the future, so we don't. And then the last event, an end event. Eventually, you're going to hit that end event that you originally scheduled. And at that point, you just move the clock forward to that time, you update your stats, and you terminate simulation. So there will be things in the event calendar, there will often be things in the event calendar after the end event. We just leave them on the event calendar. We are not allowed to look ahead in the calendar. We still schedule them even though they happen after the event calendar. So as we process things based on what the current time is. Okay. Questions about that process, about those three events? Those are basically the three events that you're going to have to hand simulate on that homework. Now, during this process, you'll have to update state variables. These are example state variables that look like the ones you'll see on your homework. So B is whether a server is busy or not. So if there's only one server, then it's only 0 or 1. How many servers are busy? There's just one that's busy. Ones that you'll see on your homework, LS and LQ. LS is the number of individuals currently in the server. So in this model, it's either 0 or 1, but if there's multiple servers, it could be higher than 1. LQ is the number of entities waiting for service. And so it could be infinite. There's no upper limit on LQ. So the work in progress is LQ plus LS. So that's the number of entities currently in the system. Uh, Entities, we're going to keep track of their arrival time. You'll do that in your homework. We do that so that when we calculate stats, when the entity has a departure, we can say, how long was this entity in here? Well, if we know the current time and we know when this entity arrived, we can now calculate how long this entity was in the system. And we use that in our performance stats and our KPIs, our key performance indicators. So in the next lecture, we'll actually do this in a hand simulation example that will look like a minimal version of your homework. But it's my claim that you have enough information to start this on that homework. So let me put up an iClicker. And then if there's questions, I'm happy to take them after here. So question I have here, I'll do a short answer. And question I have is, what are inputs to discrete event system simulations? I'm looking for a single word, a plural word. What are the inputs to discrete event system simulations? It could be something that starts with an E, it could be something that starts with an A, could be something that starts with a D. So those are some sort of examples of right and wrong answers. So what are the inputs to our DES models? Otherwise, I don't have anything else for you today. So feel free to head out after that, or if, like I said, if you have any other questions, I'll be up here. Thank you.